and orthogonal complement with respect to orthonormal basis. So in short form, I would like to call orthonormal basis ONB. O for ortho, N for normal, B for basis. So we will take orthonormal basis with respect to that. We will try to explain. So outline of my today's lecture are the following. First, I would give a recap of orthogonal basis, what we had already seen, and the relation of inner product with respect to every orthogonal basis. I had already mentioned that if you change your basis, then definitely uh, your basis, if it happens to be orthonormal, talk here today that inner product is invariant with respect to orthonormal basis. So if you take orthonormal basis, first orthonormal basis take as a standard basis, it happens to be orthonormal basis. And if you find inner product of any two vector x and y, whatever quantity you will get it here, suppose you call it alpha, you got alpha, then same alpha would be you will get when you take inner product of x and y with respect to another non-standard orthonormal basis. So that due to that it simply says that if you change basis to orthonormal basis, any standard basis to orthonormal basis, then it simply says that angle is not changed between the vector, any given vector. So angle, so also you know from your high school that dot product is always talking about angle between two vectors. So angle is invariant with respect to change of orthonormal basis. So if you're changing one basis to orthonormal basis, one orthonormal basis to another orthonormal basis, then you will observe that your inner product will be invariant, or correspondingly you can say that your angle between the vector would be invariant. So that is the main conclusion of studying inner product with respect to various orthonormal bases. Then I will talk about orthonormal projection. We will define with respect to orthonormal. We will talk about orthogonal projection with respect to orthonormal basis, and also few geometry would be there. We know that because every linear transformation is having a geometry, so that's why it is very much essential to talk about geometry of transformation. Then at last I will discuss about orthogonal complement. So orthogonal complement is somewhat, it is related with four fundamental subspaces that we had already seen that if you are finding row space of a matrix that we call it row space of A happens to be column of A transpose, and what is it is perpendicular to null space of A. That means it is talking about the second part of fundamental theorem of linear algebra. So where because we know that if you take any vector from null space of X, that would be perpendicular to every vector from the row space of A, or simply you call it column space of A transpose. Why I am calling it row space? You know that A transpose in A transpose, column of A transpose happens to be row of A. So that's why column of A transpose you can call it row space of A matrix A. So that's way. So here if you take any vector X from here and any vector Y, by default blindly you can say that the product inner product between these two would be what? 0. Why? Because these two would be perpendicular to each other. Easily you can relate these two things. So that's where if you call this row space of A V vector subspace V, then what would be name of null space of A? You can call it V perp, and this is notation of orthogonal complement. Why? Because if you sum if you do Minkowski sum of V with V perp, it will be given, it will give complete dominant space. Whatever underlying space there would be, it will give that way. That's way. That means it is one kind of you observe complementation. Complementation, it says that if you take any element from X from here, then this X is breaking. It is decomposed into two factors. One factor we are calling it X parallel. That one is projection part, and X perp, that one is perpendicular part. So X perp is coming in orthogonal complement, and X parallel is coming in V. That means row space of A. So, or you simply, you can also say that it is projection. It is talking about projection of X. So those kind of things we will study in detail here. So coming to recap of last class, orthonormal basis and its relation with inner product. So in last class we had already seen that with respect to a standard basis, if you are taking a standard basis where basis element happens to be E1, E2 up to En in n dimensional Euclidean space, and you are taking any two arbitrary vector xy, then we can represent xy in term of the basis element, and it happens that coordinate of x here coordinate vector of x with respect to a standard basis happens to be the vector itself. Similarly, coordinate vector of y with respect to a standard basis happens to be y itself. So this is the scenario of a standard basis. And when we had a standard basis, then with respect to a standard basis, if we are willing to find coefficient this coordinate, then what is happening? So this one is this coordinate you can get directly by taking inner product of x with corresponding basis element. So this one is giving your first coordinate x1, and similarly x2 would be what? X2 would be dot product of x with second basis vector E2, and x3, like easily you can get, you don't have to solve system of linear equation. And similarly xn would be what? How you can get xn? You take x, do dot product or inner product with nth basis element, you will get xn. So this is the idea to get coordinate of a vector with respect to a standard basis directly. So this is the idea, and this one is the coordinate approach, finding coordinate. This is the inner product approach. So inner product of any two vector with respect to a standard basis, how we define. So these are all calculation, and it is simplified to, it is talking about summation of component wise multiplication. That means if you are taking talking about one time 1 into 2 plus 2 into 1, and 2 will multiply with this second coordinate. So 1 into 2 into 2 plus, here it would be 2 plus 2, resultant is 4. So dot product of vector 1 2 and 2 1 is 4. You are getting directly like that. But if you want to visualize analytically how it is happening like this way. You do in a product like this way, x transpose y. That means you multiply. You try to visualize from matrix perspective. So you multiply row 1 2 with column 2 1. It is like it is algebraic visualization. It is directly coming from definition, but you also need to visualize how it is happening. So it is 1 you have to multiply with 2, and because it is this one is what? It is 1 by 2 matrix. If you try to see from the matrix perspective, row vector happens to be 1 by 2 matrix, and column vector happens to be 2 by 1 matrix. So 1 times 2 is 2, plus 2 times 1 is 2. So equal to 4. Same thing you are getting. So that's why we are calling inner product of x y is nothing, just it is talking about projection of x over y or vice versa. So this one was the story of standard orthonormal basis or a standard basis. A standard basis happens to be orthonormal basis. Now we are coming to one non-standard basis, which is orthonormal. That means this orthonormal basis will have the same feature what standard basis used to have. So we are taking non-standard orthonormal basis of n-dimensional Euclidean space Rn, and with respect to that we are defining inner product. So here we consider orthonormal basis having basis element u1, u2 up to un, and we will see the following representation. So if you are taking any vector x then if you are you know that till now I think you might already used to of finding coordinate of any vector with respect to a given basis. So what how we do? So we represent X as a linear combination of the basis element, two basis element. So we have already represented, and after solving this uh, equation, because X would be given here, so we solve it, and from there you will get your alphas. That means here what you have to solve, you have to solve V, capital V. Capital V is a mat. Don't write capital V here. I have given you notation to write U. So notation must be compatible with everyone. It would must be compatible everyone. So U time alpha. So U is what? U is a matrix having column vector U1, U2 up to UN. And alpha is a n-dimensional vector having coordinate first coordinate alpha 1 and nth coordinate alpha n equal to x. X is your given vector. X is n-dimensional given vector. So here x is given, u is, you know, just you have to find alpha. So how you can find? So apply Gaussian elimination method and solve it. Write the augmented form. You know that one is the approach. But that one is old approach. We want to go for that approach. Uh, what we will do then here? We will enjoy the benefit of being orthonormal basis. So here with respect to orthonormal basis, what would be alpha one? Alpha one you can directly get two dot product of X with first basis element, orthonormal basis element U1. Do dot product with U1 because it is easy to find. You know about X, X would be given here. You know about U1, then easily you can calculate this dot product. And if you find dot product of X with U1, that will give your alpha. How? You can see here, if you do dot product of UI but others, in other case, what you will get? Zero. Everything becomes vanish. Except alpha one, everything will become vanish when you take inner product of x with u1. So likewise zero. So you got your first coefficient. Similarly, if you are willing to get the second coefficient, what you will do? You will take u2. And likewise, if you are willing to calculate alpha n, just take dot product of x with un. Then this will give your alpha n. So it is easy to calculate coefficient of a given vector with respect to orthonormal basis because you don't have to your coefficient using dot product. So this thing I had already explained in this one. So you are directly how you are getting alpha one. So you by multiplying vector u1. Change it notation u1. All these are u is u1 uj. Okay, fine. And what is the again? If you are willing to write inner product of x with y with respect to this orthonormal basis, what would be that? It would be just component wise multiplication of corresponding coefficient or coordinate with respect to extended basis. No more here. Remember that here. No more we are taking coordinate of given vector with respect to extended basis. We are taking coordinate of given vector with respect to orthonormal basis. So your x with respect to orthonormal basis, then do component wise multiplication and sum it up. Then you will get your inner product with respect to given standard basis. So that is the idea to calculate standard basis. So everywhere change it u, replace here everywhere replace v by u. Just I change here notation for some purpose I have changed. So change u by v. Okay. So I have taken few example here. You can look into in R2. So in R2, what we will do, we find inner product of a given vector, given two vector. Actually, to find inner product, you need two vectors. So you will find inner product with respect to both two bases. First basis is extended basis E, second basis is orthonormal basis U. Some kind of orthonormal basis should be here. So here we consider orthonormal basis is this one is the orthonormal basis. Having first basis element is 1 by root 2, 1 by root, and second one is minus 1 by root 2, 1 by root 2. So if you try to visualize this one, where is these two basis element? So 1 by root 2, 1 by root 2, that means it is somewhere here. This one is 1 by root 2, 1 by. And where would be minus 1? See that the angle between these two basis element is 90 degree. So that's why these two are orthonormal. Also, if you are willing to find the norm of these two are uh, 1. That means length of these two vector are 1. So that's why these two are unit vector. These two u and u2 are unit vector and both are perpendicular to each other. From the graph also you can observe that. So call it x1 axis. This one is vertical, one is x2 axis. Now we are taking two vector. First vector is 1 2 and second vector is 2 1. So these two are given, and we will try to find dot product or inner product of x and y, first with respect to a standard basis and second with respect to orthonormal basis. And then what will happen? So what we, in order to find inner product with respect to a standard basis, what is the first step? In first step, we have to represent the given vector 1 2 with respect to this standard basis. That means we are here applying change of basis rule. So what would be coordinate of this vector with respect to a standard basis? That means you are solving this system of linear equation. So here I had already told that you can enjoy the benefit of orthonormality of the given basis. So through that, you don't need to solve this system of equation directly. You will get alpha 1. What would be alpha 1 is u1. What would be 1 by root 2 plus 2 by root 2. That means total is 3 by root 2. You are getting 3 by root 2. Similarly, if you take, you are calculating, you want to calculate alpha 2, what would be? It would be dot product of x with second orthonormal basis vector u2. So dot product, that means minus 1 by root 2 plus uh, 2 by root 2. So total would be 1 by root 2. So this one you got alpha 2. So that means alpha 1 is giving first coordinate of vector x with respect to orthonormal basis O. So that one is 3 by root 2, and alpha 2 is giving second coordinate of vector x with respect to standard basis. Sorry, with respect to orthonormal basis O, that is 1 by root 2. So you got the coordinate vector of x with respect to this basis, orthonormal basis. You got. Similarly, this is short notation of writing way of similarly. So similarly, you can find a coordinate vector of given vector y. Y is what? 2 1. So what would be coordinate vector of this one with respect to this orthonormal basis? It would be 3 by root 2 and minus 1 by root 2. So you got the coordinate vector. Now we will try to find two things. First is we will find inner product of x y with respect to standard basis. See here, standard basis. We are finding with respect to standard basis. So what is standard basis for R2? Again, I would like to write it here. So this one is the standard basis of R2. So if you find a standard basis of inner product of x, y with respect to a standard basis, what do you do? Just, these are the coordinate of a vector with respect to a standard basis happens to be the vector itself. So you don't need to calculate coordinate here directly, it would be the same. So just do coordinate wise multiplication. So 1 time 2 plus 2 time 1 total. That means 2 plus 2 equal to 4. you got 4. 4 is the inner product of this given vector xy with respect to standard basis. Now try to come across to find product of xy with respect to standard basis. So that's why you have to take coordinate vector of x and y with respect to orthonormal basis O. So what is the coordinate of x with respect to orthonormal basis? It is 3 by root 2 1 by root 2, and coordinate vector of y with respect to orthonormal basis O is 3 by root 2 minus 1 by root 2. So if you do component wise multiplication, then summing it up, what you will get? 3 by root 2 into 3 by root 2, that means 9 by 2. And 1 by root 2 into minus 1 by root 2, you are getting minus 1 by 2. So if you sum it up, then what you will get? The result is 4. That means inner product of same vector with respect to orthogonal basis, it is coming 4. Both are equal. Both are equal. So what does it say? It simply says that inner product is invariant with respect to orthonormal basis. Invariant with respect to orthonormal basis. That's why we are getting the same inner product. If you are, suppose it happens that O is not orthonormal basis, that means there is definitely an angle between uh, angle which would be either less than 90 or greater than 90 between U and U2. That time this would be not preserved. So that time you have to be very careful during that process. Okay. So angle is always preserved here. In case of orthogonal basis, angle is always preserved. So also during the basis which is not orthonormal and neither standard, and then that time you have to be very careful while calculating inner product. That time one positive definite matrix would come in order to compensate compensate this dot product. So that one is little bit complicated. I won't talk about that thing here. It is beyond of this course. So here you have already seen that inner product is invariant with respect to orthogonal basis. So here in this model we will study one concept that whatever basis you are taking, non-standard basis you are taking, you can always transform that non-standard basis into a orthogonal basis, and that property, that concept, we are calling it Gram-Smith orthogonalization process. Those things we will study in detail in this module. So whatever, just blindly whatever, take any non-standard basis and apply Gram-Smith orthogonalization, and definitely you will see that you will get your orthogonal basis with respect to any non-standard basis. So that is the ultimate aim of this module. So another example I have taken, but the basis is same. This one is the orthonormal basis. Now you are taking here vector is change. We are taking 1 0 and 0 1. So what is the dot product between 1 0 and 0 1? It would be 0 with respect to a standard basis. Now, but if you are willing to calculate a inner product of x and y with respect to this respect to orthonormal basis O, so coordinate of 1 0 is what? 1 by root 2, 1 by root 2. So you got the coordinate of x and y with respect to O basis O. Then we will find dot product. So inner product of x y with respect to a standard, easily you can find 1 time 0 0. Similarly, if you are willing to calculate coordinate vector with respect inner product with respect to orthogonal basis, what would be 1 by root 2 times 1 by root 2, that means 1 by 2, and then minus 1 by 2 times 1 by root 2, that means here it will be what? See here calculation, see the calculation, how calculation is happening. So in the second, with inner product with respect to orthonormal basis is coming what? 1 by 2 minus 1 by 2, and that means 0. We are also getting it 0. So that means it says that again the angle is preserved, or you can simply say that inner product is preserved under orthonormal basis. If you change basis from one orthonormal basis to another orthonormal basis, then the angle between the vector, it will not change. That is the ultimate aim of change of basis with respect to orthonormal operation, orthonormality. So now coming to discuss about orthogonal projection with respect to orthonormal basis, how we can relate orthonormal projection to orthonormal basis. So those things we'll discuss it here. So we had already seen that if we are taking a vector x in R2, then first thing here I am going to discuss about orthogonal projection of 2D vector along a line or to a line. So suppose x we are taking any arbitrary vector in R2 and L is a line in R2. Then when we are calling L is a line, then definitely it will have a direction. We'll talk about, because line is a unidirectional. It is having a line is a one-dimensional uh, subspace in R2. Even anywhere, line happens to be one-dimensional subspace. So line is, so definitely if it is one dimensional, that means it is having, line is having only one direction. Meaning of one dimension means only one direction. So if x is a any arbitrary vector in R2 and L is a line, then we can resolve the vector, this arbitrary vector x into two components. First component is, we are calling it x parallel. That name of this one we are calling it, we call it projection of x along the line. So we are projecting along the line, and that one happens to be parallel to L or in the direction of L. Parallel to L means simply you can say that in the direction of L. And second component is x per. X per part is, it would be perpendicular to the line. That is, we have decomposed the vector x into two components, x parallel plus x per, or that means projection of x plus x per. And this representation is unique up to each basis. So, this representation is always unique. Up to, I mentioned that if you change the basis, you will get definitely same thing, but their representation would be different. So unique up to each basis. So here I have taken, so nothing is mentioned there. I had already mentioned that what would be basis? Basis is your standard basis. So here x vector you have already taken. Then you can observe that this one we are calling it projection of x with respect to this line. This one is the projection part, projected part. This part. This one is the what, x per part, perpendicular. So you can easily see that if you allow projection of orthogonal projection operation, then always you can get two vector, two component. So here both component happens to be perpendicular to each other. Why? Because we are here basis we have taken standard basis, and standard basis is the angle between that means every basis element are perpendicular to other basis element. So that's why here we observe orthogonalities. This orthogonality, it is implied from the orthogonality of the standard basis. So that's why it is coming here. If suppose the basis element happens to be not orthogonal, then we can't talk about orthogonality between these two components. So it is simply, you can say that orthogonality here it is coming with, due to orthogonality of the basis element. Here a standard basis is what? The standard basis here in R2 is 1 0 and 0 1, and we know that angle between 1 0 and 0 1 is 90 degree. That's why angle between projection of x parallel and x per is 90 degree. Due to that it is happening. Okay, so we'll go to see further. So if you are coming to discuss about orthogonal projection to a plane in R3, then again what we do, take any general any arbitrary vector x from R3 and plane. What is plane? Plane happens to be two-dimensional symmetrical object. So that means when you are calling it two-dimensional, it will have two bases. Two direction means two bases, or two simply you can say that, or further you can basis direction. So further here we can resolve the arbitrary vector x into two component. One component it would be perpendicular to the plane, this plane. Another component would be on the plane. So on the plane part we are calling it projection part, projection of x. So this is the on the plane. So you have taken any x. So this is the projection of x on the plane, and this is the perpendicular part, perpendicular to the plane. So this we are calling it x per. This is x per. this one is x parallel. X parallel. So we always here we again we are able to see that the angle between these two component x perp and x perpendicular parallel, that means projection of x and x perp is what 90 degree. Why? Because basis here we have taken a standard basis. So that's why it is happening. Again, I would like to recall the standard basis is 1 0 0 last basis element of this E, it would be 0 0 1. So you can see that angle between each basis element is what 90 degree, and also these are unit vectors. X is given for given x, how we can calculate projection of x in the direction of on plane or in the direction of line. So those kind of things we have to calculate. So directly we will calculate it with the help of inner product with respect to uh, basis, orthonormal basis, that we will calculate it here. So one example here I have taken. So the formula for finding orthogonal projection with respect to a basis. What is the formula? So consider we are having a subspace k-dimensional subspace of Rn. That means V is having a basis which will have so take a, it will have a basis which will have k number of elements. So we are taking a very specific basis. That one is orthonormal basis. So every vector space can have orthonormal basis. Every vector space is having orthonormal, but remember that don't take standard basis. And every vector space is having non-standard orthonormal basis. We can either we can easily get it or we need to construct it. So and arbitrary vector, if you take any arbitrary vector x from Rn, then we will try to find projection of x with respect to this orthonormal basis. How we can get it? Orthonormal basis. So just what you do, you know that this projection part of x, this projection part would be linear combination of basis element of V. So that means you are saying that x1 times u1, because it is in the plane V. So definitely it would be linear combination of basis element of V. So alpha 1 times u1, alpha 2 times u2. Likewise, you will go up to plus alpha and alpha k times basis element. So that's why you will get up, you will go up to, how can you find alpha, this coefficient alpha 1, alpha 2 and alpha k? So you can find it again. Alpha 1 would be dot product of x with u1, alpha 2 would be dot product of x with u2. So this one is alpha 1. Directly you are just finding with the help of dot product, you are easily getting your coefficient alpha 1, alpha 2 and alpha k. Similarly you will get how? By taking dot product of given vector x with uk. So you got the coefficient directly you got. So suppose I have this example specifically I have taken here. Here suppose V is x1 x2 plane. It is two-dimensional x1 x2 plane. That means this one is x1 axis, this one is x2 axis, and this one is x3 axis. Okay, so here this plane is talking about x1 x2 plane. This is x1 x2 plane. And what is the basis of x1 x2 plane? So take a standard basis as an orthonormal basis for simplicity. This one is 1 0 0 1. It is the basis of plane V or subspace B. It is the basis of subspace B. So now what we do, we have taken any arbitrary vector x. So x is here. So what is the projection of x on the plane? So if you try to see, this is the projection. This is your vector x. X. Then if you project it on the plane, this is the projection of x on the plane. So you can call it projection. We also denote it x parallel. So this is the projection part, and this is what, this is your x perpendicular part. You can observe that the angle between x per and x parallel, both angle between this is 90 degrees. You can observe there is a 90-degree angle between these two. So you can say that what is this one? So it is coming in x1 x2 one is x perp equal to x1 x2 0. That means you can say that x1 times 1 0. So your alpha 1 is, but here you can call it in term of u1. This one is u1, this one is u2. Okay. So and what is alpha? So how you will get? So if you take dot product of x with u1, it will give your alpha 1. What is your alpha 1? Alpha 1 is your x1. Similarly, dot product of x with, right now remember that I am talking in general perspective. That's where these things are coming. So if you take dot product of x with u2, what you will get? X2. So in that process, you are getting your x per x1, x2, and you don't have third coordinate, so you can directly put it 0. 0 time u3. U3 is not. Why? It is talking about 0 time u3 means it is talking about absence of u3. So this is the projection part. So one more example I have taken it here. So consider a subspace of R4. R4. So what is subspace here? Some subspace of R4 is, it is a two-dimensional subspace as an image of this matrix. So simply you can forget about this matrix. You can say that this one is a V is a subspace with basis. This is the basis of this subspace. It is having two basis element u1 and u2. You can observe that. How can you normalize it? What is the angle between? Call it v1, v2, and call it, this one is u1. It is already written u1. So u1 is what? So after normalization, you are getting u1. So u1 is v1 divided by norm of v1. That means unit vector in the direction of u1 divided by norm of or length of u1. And u2 is what? u2 is v2 divided by norm of v2. Norm of v2, and then you will get it. So tell me, what is the angle between v1 and v2? Anyone would calculate angle or dot product, inner product? What is the angle between v1 and v2? Calculate easily. What is the inner product between v1 and v2? 1 time 1 plus 1 time minus 1. That means 1 minus 1, 1 time minus 1, further minus 1, and 1 time 1 plus 1. So here 2 minus 2. It is coming as 2 minus 2. The result is, final result is 0. So that means you can say that v1 and v2 are perpendicular to each other. Similarly, normalizing, after normalization, you are getting u1 and u2, and you can easily observe that these two are again perpendicular to each other. Apart from that, here norm of u1 and u2 are 1. So it is a orthonormal basis. It is you can say that it is a orthonormal basis. So we are taking any general vector, uh, four-dimensional vector 1, 3, 1, 7. So we will try to find orthogonal projection of this one on this plane. So what would be orthogonal projection of this one on the plane? And that means if you are willing to, this point may not be in the plane V, but it is a four-dimensional point, any four-dimensional point. So it is here in R4, but we don't know whether it is in V or not. So we have to, it is not necessary to know whether it is in V or not. So what we have to, it is, if it is in V, what does it say? It simply says that it would be linear combination of these two elements, the basis element. Otherwise, if it is not V, then it would be not. We can't write as a linear combination of these two. It will be linearly independent of these two. That is the criteria. But here, question is different. Question is that we have to find orthogonal projection of this vector on this subspace. How you can find? So just we will represent this projection of x on the plane V. It would be a linear combination of u1 and u2, and coefficient would come from dot product of x with u1 and dot product of x with u2. So just do dot product of x with u1. What would be that? It would be 3. And dot product of x with u2, it would be 1. So finally, you are, sorry, dot product of x with u1, it would be 6. And dot product of x with u2, it would be. So that's why 6 times u1 plus 2 times u2. Finally, you are getting it. This is the projection of this vector, given vector x, with respect to this plane. So you can easily verify that you can say that this one is a linear combination of these two vectors. Here it is talking about. This relation itself, it is talking about this projection part of this part of x is a linear combination of these two u1 and u2. That means you are saying that this projected part of x is in the plane V. So that is the idea. So here you got one more interesting approach to calculate projection of a given vector with respect to a plane with the help of orthonormal basis. So what is the step? So in order to calculate that, first you have to find orthonormal basis of the given subspace where you want to project a given vector. So first find orthonormal basis. Then second, what you do? Coefficient, how you will get? Coefficient get, so suppose x is given vector. So find the dot product of x with each basis element. That would give your, so I am writing ui. That take dot product of given vector x with ui, what it would give, it would give alpha i's, and then make a linear combination with respect to this alpha I. So you can say that you got your projection of x, with respect to subspace V is what? You can simply say that it is alpha 1 times first basis of subspace V, alpha 2 times second basis of subspace V, likewise alpha k times kth basis of V, uk. So this is the approach to find projection of a given vector with respect to subspace and orthonormal basis. So this is the approach. In next class, we will discuss in detail about further orthogonal complement is a simple. It is not very tedious task. So you had already got the idea of orthogonal projection with the help of orthonormal basis of a subspace. So what is, so it is coming in the subspace. It is coming in the subspace. Then where does it go? Where does it go? So it is coming in the image space, or subspace. You can say that image space of T. And where does this one go? This go to kernel of T. This go to kernel of T. So that's why this kernel of T it will give orthogonal complement. So in next class I will discuss in detail. I mean, this is the definition of orthogonal complement. So what you do, you revise the concept of kernel, and in next class I will discuss in detail regarding this concept, and I will start grammar Smith orthogonalization.